Another important technique for analyzing molecules is a technique called mass spectrometry. Fundamentally, this is a very simple technique because all we're doing is measuring the mass of the molecule. So how do we measure the mass of a molecule? Well, first we introduce the sample into the mass spectrometer. The part of the instrument into which the sample is introduced is under extremely high vacuum, so the sample vaporizes. It's then necessary to convert them into molecules with a positive charge, which are called ions. One method to convert molecules into positively charged ions is to bombard them with electrons. So the molecules now have a positive charge. They pass through a slit and are accelerated by a high voltage. After they've been accelerated by the high voltage, they go into an area of the instrument which is in a strong magnetic field. So as these ions go into the magnetic field, they are deflected off their straight course and they curve. They go through this part of the instrument and then they reach the detectors, where their arrival generates a signal which is recorded. Now, how does this separate the molecules according to their mass? Well, it's very simple. If you have a very light molecule, once it is charged and it goes into the magnetic field, because it's light, it's deflected a great deal. So there's a large deflection from the straight course. If you have a big molecule, it's deflected a lot less. So we can measure the mass simply by measuring the degree of deflection in the mass spectrometer. How do we know what molecules weigh? Let's take an example of the molecule of cocaine, which is shown on the screen. Cocaine has the molecular formula of C17H21NO4. Now, each carbon atom has an atomic weight of 12. So carbon will contribute 204 to the molecular weight of cocaine. Each hydrogen atom has an atomic weight of 1. We have 21 hydrogens, so hydrogen will contribute 21 to the molecular weight. Nitrogen has an atomic weight of 14. We only have 1 nitrogen, so that adds on 14 to the total. The atomic weight of oxygen is 16. We have 4 oxygens, that adds on another 64 to give us a grand total of 303. So if we take an unknown sample and we put it in our mass spectrometer and we get a molecular ion with a weight of 303, does that mean it must be cocaine? The answer is no. It does not prove that it is cocaine. And the reason is that if you have this many atoms, there are many, many possible ways you can arrange those atoms to make your molecule. These different possible arrangements of the same atoms, the same C17H21NO4, are called isomers. Only one of these isomers is cocaine, and therefore only one of these isomers is illegal. So simply putting a molecule into a mass spectrometer and getting a number, the molecular weight of the molecule, does not prove that it is this particular compound, simply because there are so many possible arrangements of this collection of atoms which would all have the same molecular weight. So, is mass spectrometry useless? No, because mass spectrometry has another trick up its sleeve. Let's think about what's happening in the mass spectrometer. A lot of the molecules, when they're bombarded by electrons, will actually break up into fragments. The fragments, of course, will have lower weight than your molecular ion, which is derived from the molecule itself. So what we'll see is a pattern of different fragments at the detectors. So we will get a mass spectrum where the highest weight will be the molecular ion, which we call M+, the molecular ion. And then at lower weights, we'll see a distribution of different fragments. Now, if we take the same compound and we analyze it by mass spectrometry under the same conditions in the same way, then each time we should get the same fragmentation pattern. So if we have an unknown compound which we think is cocaine, we run the mass spectrum and we look at the fragmentation pattern. We analyze an authentic sample of cocaine. We compare the two fragmentation patterns. If they're the same, then we conclude this really is cocaine, because if we have an isomer of cocaine, it would fragment in a different way, and therefore it would give us a different pattern. So here, for instance, is the mass spectrum of cocaine, and you can see on the right-hand side there's our molecular ion at 303, the same as when we added it up from the molecular formula. And then you can see this quite detailed fragmentation pattern, which is characteristic of the cocaine molecule. Below it, you can see the mass spectrum of diamorphine. Again, on the right-hand side, there's our molecular ion. And then at lower weights, you can see this very nice fragmentation pattern. So we have chromatographic techniques which will separate our mixture into its component parts. And we have spectroscopic and spectrometry techniques which will identify those components. We can combine separation and identification into a single instrument. And the instrument that is most widely used for this in forensic science is the GCMS, gas chromatography mass spectrometry. This is sometimes referred to as a hyphenated technique because it's GC-MS. So you can see here an example of a GCMS. The way it works is that the output from the GC, the end of the column where the components come out, feeds directly into the mass spectrometer. So the mass spectrometer acts as the detector for the different components. So when we analyze the data, when we look at our GC chromatogram, not only do we see the retention time, not only can we quantify it by the area under the peak, but we can also access the mass spectrum for that GC peak and do the identification. So GCMS combines separation of the components and identification of the components. So we have a number of techniques for chromatography, particularly TLC, GC, and HPLC. Each one has their own particular advantages and disadvantages. But each one is simply there to separate a complex mixture into the individual components. Once we have the components, then we have two very powerful techniques for identification. We have infrared spectroscopy based on the molecular vibrations, and we have mass spectrometry where we use the fragmentation pattern of the molecule. And we can even combine our separation technique, our chromatography, with our identification technique, most commonly our mass spectrometry. And we can combine those into a single instrument. And this is one of the most important instruments for the forensic scientist.